Welcome, my friends! Consider the expression the square root of 20, which we are asked to simplify. 20 is not a perfect square, meaning there is no whole number that can be squared to get 20. But the square root of 20 can be rewritten as the square root of 4 times 5, and 4 is a perfect square. One of the properties of square roots is that if you have two numbers multiplied underneath a square root, it can be rewritten as two separate square roots multiplied together. So the square root of 4 times 5 can be rewritten as the square root of 4 times the square root of 5. Well, we know that the square root of 4 is 2, so we can rewrite this as 2 times the square root of 5, or more commonly, just 2 square root 5. This is the process you should use whenever you have a square root in your final answer of any problem. The square root of 20 is not considered to be in simplified form, but 2 square root 5 is. Let's try another one. We have the square root of 2 times the square root of 48. As I said before, one of the properties of square roots is that if you multiply two square roots together, you can multiply their insides. So this can be rewritten as the square root of 2 times 48, which is just the square root of 96. At this point, you will want to think of the perfect squares, which are 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, 5 squared equals 25, 6 squared equals 36, 7 squared equals 49, etc. And you want to see if you can break 96 down into a perfect square times a number, ideally the largest perfect square possible. After thinking for a moment, I realized that the square root of 96 can be rewritten as the square root of 16 times 6. This can be rewritten again as the square root of 16 times the square root of 6. We know the square root of 16 is 4, so our final answer can be written as 4 times the square root of 6, which is our final simplified form. Now I want to show you what would happen if you didn't choose the largest perfect square. 4 is also a perfect square that we could have used here. We could have had the square root of 4 times 24. That's the same as 2 times the square root of 24. But the square root of 24 is not fully simplified. This could be further broken down to 2 times the square root of 6 times 4. At this point, the square root of 4 could come out as a 2, which would multiply the 2 that's already there, and then we would have 2 times the square root of 6, which is the same thing as 4 times the square root of 6, the same answer we had the first time. So it isn't an issue if you don't pick out the largest perfect square. You'll still get the same answer, but you might have to do a little bit more work. Okay, let's try one more. We have the square root of 180. Here is the list of perfect squares. None of the really big ones jump out at me as definitely working, but I know 9 will work. I can break this into the square root of 9 times 20, which is 3 times the square root of 20. Now I know 3 square root 20 can be rewritten as 3 times the square root of 5 times 4. The square root of 4 can come out as a 2 and multiply the 3 so that we have 6 times the square root of 5, which is our final simplified form. It turns out that the square root of 180 can actually be rewritten as the square root of 36 times 5, which simplifies to 6 square root 5. So 36 is the perfect square we could have used to do this in one step. Of course, you might not always recognize the largest perfect square, and that's fine. It just means that you might need to go through the process a few more times. Let's try this one. The square root of 27w to the 14th power. We can rewrite this as the square root of 9 times 3 times w to the 14th. Now, both 9 and w to the 14th are perfect squares. The square root of 9 is 3, and the square root of w to the 14 halves the power, so that we have w to the 7th. We still have the 3 left underneath the square root, since 3 is not a perfect square. Altogether, we have 3w to the 7th square root of 3. How about the square root of 12y to the 7th? This time, both 12 and y to the 7th are not perfect squares. A variable is only a perfect square if it is raised to an even power. But 7 is an odd number, so y to the 7th power is not a perfect square. We can break this into the square root of 4 times 3 times y to the 6th times y, as y to the 6th times y is just y to the 7th. Now we have both 4 and y to the 6th, which are perfect squares and can be pulled out. We have 2, which is the square root of 4, and y to the third, which is just the square root of y to the sixth. Inside the square root, we still have 3y, so that our final answer is 2y to the third square root of 3y. Let's try the square root of 50x to the 8th, y to the 5th. X to the 8th is our only perfect square. Y to the 5th has an odd power. We can rewrite this problem as the square root of 25 times 2 times x to the 8th times y to the 4th. The square root of 25 is just 5. The square root of x to the 8th is x to the 4th, and the square root of y to the 4th is y to the 2nd. We still have 2y, which are our two terms that were not perfect squares, still in the square root, so that our final answer is 5x to the 4th, y squared, times the square root of 2y. Let's try 3 square root 80 plus square root 20. Now, you can think of square roots kind of like variables, in that the only way we can add or subtract them is if the square root is the same, which is not the case in this problem. Let's try simplifying the square roots. 3 square root 80 can be rewritten as 3 times the square root of 16 times 5, and the square root of 20 can be rewritten as the square root of 5 times 4. The square root of 16 is 4, so 4 times 3 is 12, making 12 times the square root of 5 for the first term. The second term simplifies to 2 times the square root of 5. Now we have two square roots that match each other. Both terms have the square root of 5, kind of like having the same variables. That means we can add the constants of 12 and 2 together to get 14 square root of 5, which is our final answer. Okay, let's try one more problem involving variables. We have 4y times the square root of 48y to the third minus the square root of 27y to the fifth. Neither of our square roots have perfect squares in them. We can rewrite the first term as 4y square root of 16 times 3 times y squared times y, and we can rewrite the second term as negative square root of 9 times 3 times y to the fourth times y. For the first term, we have the 4y that was already there, but then we have the square root of 16, which is 4, and the square root of y squared, which is y. On the inside, we still have the square root of 3y left over. For the second term, we subtract the square root of 9, which is 3, and then we have the square root of y to the fourth, which is y squared, leaving us with the square root of 3y on the inside. Simplifying the 4y times 4y, we have 16y squared, square root of 3y, minus 3y squared, square root of 3y. Our two terms match both inside the square root and out. We have y to the second power outside each square root, and 3y on the inside. That means we can subtract our square roots to get 13y squared, square root of 3y, which is our final answer. Alright my friends, that completes our video discussing radical expressions. Join me in the next video where I will discuss more properties of radical expressions, as well as equations involving square roots.